All right, why don't we go ahead and get started here with today's seminar. For those who don't know me, my name is Roy Barnes. I'm a professor here at the University of Washington, and it's my great pleasure to introduce today Professor Karyn Rogers from the Rensselaer Polytechnic Institute. Karyn has had a long and illustrious career in science, starting first at Harvard at the Earth and Planetary Sciences Department, where she also was in the Environmental Science Policy program as well. She then went to the West Coast and got a master's degree in Stanford before moving to the middle of the country to get a master's degree and a PhD in Earth and Planetary Science from Washington University in St. Louis. She then took a postdoc at Woods Hole and then took a professorship at the University of Missouri before finally arriving at RPI in 2013. As you'll see, in addition to all the great science that Karyn has been up to recently, she is also the PI of a big collaboration known as the Earth's First Origins Project, which is the title of her talk today. She's also the director of RARE, the Rensselaer Astrobiology Research and Education Center at RPI. And she's also one of the co-leads for the PCE3 RCN. And to disambiguate that, that is a research coordination network known as the Prebiotic Chemistry and Early Earth and Environments. So before I turn it over to Karyn, just a couple quick points about the format today. Please, if you haven't already done so, please mute your microphone and turn off your video. And if you have any questions for Karyn during the talk or afterwards, please type them into the chat room, and I'll be reading them at the end to her so she can answer them, and we can streamline that Q&A session at the end. So with that, I'm going to turn it over to Karyn so she can tell us about a new paradigm for searching for life's origin. Professor, please take it away.
Thank you very much, Rory. I really appreciate it. And I want to thank all of you. I was really excited to come out and see you. I was really disappointed that I couldn't come out and see you, but this has been a really good day. I'm pleasantly surprised at how virtual is working so well for this. I really have enjoyed my visit. I do hope to come and see you guys in person at some point. But in the meantime, this has been a really, really good day, and I'm excited to be able to share some of this with you. So thank you in advance for all of that. So what I want to do today is tell you a little bit about what we're doing here at Rensselaer and with the big consortium project on Earth First Origins. But it wouldn't be right if I didn't give a talk with data. And so I have sort of an outline for my talk, but it's different than an outline normally looks. This is my talk outline. It's going to come in two pieces. The first part, I'm really going to give just some background about the Earth First Origins project, a little bit of background on origin of life and prebiotic chemistry research in general. And then I will transition away from that and talk about some of the sort of preliminary work we've been doing on this project in the last few years. And so literally my slides are separated between a white background and a black background. And so this is why you have this outline this way. So I'm hoping that will serve as a bit of a roadmap for going through this. And so I want to get started first just by, oops, I think sorry, I went too far. There we go. Just by talking a little bit about how, in general, the scientific community has approached origins of life research. There is largely the top-down approach and the bottom-up approach. And from the top-down approach, right, we start with modern life, and we do our best to look backwards, right? So we start with modern life, modern biochemistry, modern environmental tolerances. That tends to serve as sort of our limits on habitability. We try and understand how the inside of the cell works, right? And so we sort of look at modern biochemistry, modern biomolecules, and we sometimes do some reversing of the genetic code to try and figure out what sort of maybe a primitive or sort of last universal common ancestor genome might have looked like, right? So that's the top down. And these boxes here are sort of color coded for how well we can know something, right? And so the top we can know really well, but as we look backwards, it gets harder and harder to understand the origin of things like chirality and membranes and biomolecule formation. On the other side of this, we're talking about a bottom-up approach, right? Where we essentially start well, you could start with the universe or the solar system, but I tend to start with the planet. And then sort of move through planetary evolution, looking at planetary environments. A lot of people will look at the earliest fossils we have, at least the earliest putative fossils we have, trying to understand something about maybe their metabolism or the environment of these ecosystems, and maybe backing up into biomolecules of interest. And again, this sort of getting from the bottom to the top also gets a little squirrely on the edges. And so what this has sort of largely led us to in Origins of Life, I'll start with this top-down approach, is something like this, right? So we start here, we start working down. It doesn't really matter in this case if you start with the chicken or the egg. Either way, you end up with a very primitive prokaryote, and then something before that that likely contained, maybe contained, all of the pieces that life now contains, right? And so here's an example of what life now contains. There's RNA and DNA and proteins and, you know, lipids and membranes and sort of metabolisms. You can see some metabolisms over here, right? And so largely what people have done is they've said, okay, well, how do I make one of these? Or maybe how do I make two of these? And what that has led us to is something like this, right? So one of the sort of principal hypotheses in the origin of life is the RNA world hypothesis, right? Which says maybe RNA was the first biomolecule because it can kind of do information storage and it can kind of do catalysis. But if you come over here to this grouping of stuff that's in a sort of primitive cell, you might find something else like metabolism. And so from that stems the metabolism first hypothesis. And then there's, of course, metalloenzymes, which are sort of replete in all of modern biochemistry. So you might end up seeing some sort of metalloenzyme world. Or, you know, you might see both RNA and peptides, and thus, you know, sort of lean toward an RNA peptide world. And so this is largely what top-down has gotten us, right? Is these and many other types of sort of ideas about how life originated. And so with this sort of approach, what generally happens, right, is that people start with modern life, they go and they look at those pieces of modern life and hear those sort of worlds or hypotheses that have developed since then. And then they go take that biomolecule or components of some hypothesis and they try and create it in the lab abiotically, right? And so let's say someone's stuck on the RNA world, they'll go try and figure out how to make RNA in the laboratory. And they'll work and they'll work and they'll work and they'll work and they'll continue to work until they really get RNA polymerization, sort of synthesis and polymerization down so it works really, really well. And then they tend to come to folks like me or folks like Bruce Watson or I actually don't know who's in the room, but if there are geologists in the room with us, they'll go to folks like you and say, okay, so these are these laboratory conditions in which I have optimized this prebiotic synthesis. And so where on the early Earth do these conditions exist? And I would say most of the time the answer is, well, I'm really glad you have those sort of lovely laboratory conditions, but they don't exist on the early Earth, right? And so there's a lot of work that goes into trying to do prebiotic chemistry, but outside the sort of necessary context of early Earth environments. So often that sort of creates, it's not really dead ends, but it creates hypotheses that really have no place on this planet. And that makes making the science move forward really kind of challenging. But there's other types of challenges as well, right? And so if we start either with the top-down approach or with the bottom-up approach, there's this other sort of pitfall that you can fall into, and folks have fallen into it, right? And so if we go top-down over here, we look at the tree of life, and one of the things we find is that all of the organisms near the root of the tree are thermophiles or hyperthermophiles, right? They're high temperature loving organisms. And so folks have seen this and said, well, that is consistent with the idea that the origin of life was in a high temperature system. And so maybe that was a hydrothermal system. And so that's literally where sort of one of the places that sort of this hydrothermal origin of life hypothesis came from. Alternatively, if you come over here to this sort of bottom-up approach on the right-hand side, we're looking at a couple of different amino acids here. And in order to make peptides, right, you need to do a polymerization reaction. In order to make a nucleic acid polymer, you also need to do a polymerization reaction. And those reactions are largely condensation or dehydration reactions. And people have said, oh, well, you can't possibly do a dehydration reaction in the presence of water. And so therefore, the only place to go would be somewhere on the surface where we can have something like a wet-dry cycle, right? Because we need this drying capability. And neither of those things are really a wrong way to go, right? These really are coming from data. The sort of the organisms closest to the root really are thermophiles. That really is pretty good. It's a pretty good argument for having a thermophilic origin or last universal common ancestor. But what this sort of approach leads to is something like this, where we say, sort of, okay, here's the early Earth. We're going to look at just these surface environments where there are wet-dry cycles. And now we have to torture them and twist them so you can actually make, ooh, hang on, wrong slide, got in there. Let me scoot forward one side. Right, here's your, sorry, wet-dry cycle. And now we torture them and twist them, and we try and make these environments make every single piece of modern life that you can. Right, and so you can do this in wet-dry cycles, in sort of tidal pools, or in terrestrial subaerial hydrothermal systems, or alternatively, you can do it in your any other favorite environment. The issue with either of these sort of ways is not just these two environments. Pick your favorite environment, pick your favorite biomolecule. What we sort of think is the issue with that is that neither of those really looks as the planet as a whole. And so what we've thought about is how we can marry prebiotic chemistry and these early Earth environments. And so usually, you know, sort of where both of these approaches have landed us is we have top down on the left, we have bottom up on the right, we have prebiotic chemistry on one side, we have early Earth on the other side, and in the middle is literally no man's land. I looked up this definition. I believe this is the Wikipedia definition. No man's land is disputed ground between the front lines or trenches of two opposing armies. And that pretty much accurately describes this community in a lot of ways, in terms of trying to sort of fight the tension between the reality of early Earth environments and the necessity of conditions of prebiotic chemistry. And so this land or area is generally unowned or uninhabited or undesirable. And that's the real hard part, right? Is that this piece in between prebiotic chemistry and the early Earth is relatively unowned, right? How do we make these two really necessary parts of the origin of life actually meet in the middle, right? How do we get these two approaches, right? Whether it's your favorite biomolecule or all of the biomolecules, and your favorite environment and all of the environments, how do we get those two things to meet so we can make the molecules necessary for life in the sequence that whatever sequence they sort of came in? And how do we do that under conditions that were really plausible on this planet when life originated, right? And it really is this middle ground that is really sort of screaming out for some advancement. And so what we've done as part of the Earth First Origins project is to say, okay, we're gonna start with early Earth, and we're going to figure out what those environments are like. And so here's a diagram that my colleague Bruce Watson put together for us, right? And it's a conceptual diagram of what, sort of a cartoon diagram of what the early Earth might have looked like. It also includes, though, a variety of environments, and we thought this was really quite important. And what I will note on here is that in this diagram, we are depicting subaerial land. I realize that that is a point of contention. It is not something that I can actually answer whether or when there was subaerial land, but we're including it here to sort of be complete in our understanding of the potential Hadean Earth environments. And so the idea behind the Earth First Origins project is understand what the Hadean environments might have been and understand what their sort of ranges and conditions might have been. There isn't one temperature, right? There isn't one salinity, there isn't one fluid composition. There's not even one temperature in a single one of these environments, right? Not only are these parameters sort of co-varying with each other, but some of them are unknown, right? And so they have sort of ranges of constraints, but we probably don't know it down to the degree or the bar or the sort of molar sodium concentration. So we get our best estimate of what these environments are like, and we build those environments in the lab. That is really the goal of this entire project, is to understand the full suite of conditions that could have occurred on the early Earth, do our best to replicate them in the lab, and hopefully at some point, what will come out of that are all of the bits that essentially make up life today. The thing about this particular approach is that no matter what we get out of all of these experiments, if we get the conditions right for the Hadean, right? If they are reasonable Hadean conditions for a particular environment at a particular point during the Hadean, right? And so that, you know, that might include a changing atmosphere over those 500 million years or whatever. But if we get these conditions right and we do this experiment, whatever chemistry comes out was chemistry that happened on this planet. Now, that chemistry may or may not have led to life, but it did happen. And so at least we know that the chemistry that comes out is realistic chemistry for these realistic conditions. And so in this project, we asked this question: how and where did life originate on Earth? And I've added a lot of words here because I think the sort of caveats to this question are really important. How did planetary processes give rise to the particular environments and conditions that enabled the prebiotic chemistry that led to life, right? We are sort of, in our group, we are largely agnostic about both the prebiotic chemistry and an environment. We don't really like the one batch, sort of the one pot model, which is sort of, it kind of litters prebiotic chemistry, right? Which is, let's make everything in all the same kind of space, all the same kind of environment. And so this plurality of environments that we mention here is on purpose, right? It is likely that however prebiotic chemistry emerged and eventually followed a pathway to life, right? It's unlikely that it was a single environment at a single time under a single condition. And so that leads us to our second question, which is, what is the viability of key prebiotic processes in plausible early Earth conditions? And how is the prebiotic pathway environmentally sequenced? And so what I mean by this is that it's sort of building on that last idea I had, is that we have to sort of we have to get essentially from a prebiotic or even an abiotic planet to something where you can make a cell. And that's not one step, right? That is several steps, probably along a reaction pathway, but also that reaction pathway is likely to follow an environmental pathway, right? So you have some reactions that are necessary for the sort of emergence of life, to make the prebiotic molecules for the emergence of life. And they can be synthesized or sequenced or selected in one kind of environment. But there's another set of compounds that are particular to a different kind of environment. So you not only have to understand how it is that environments sort of can change with time and can change with condition, but you also need to understand how environments are connected and how molecules might move from one environment to another. And so all of that is part of the question we're trying to ask. What particular environments support what kind of prebiotic chemistry, and how do we put all of those together to go from an abiotic planet to a prebiotic planet to a biotic planet where we have made the abiotic-biotic transition? And so that's largely what we're aiming for in the Earth First Origins project. To do that, we need to know something about the Hadean. And so for those of you who don't sit around and think about sort of the geologic timescale on a regular basis, I have the easiest version of the geologic timescale here. We start when we accrete the planet. The Hadean probably looks something like this lovely image that Simone Marchi has created. And then sometimes around 2.5, we actually get oxygen, and maybe the planet kind of looks like what we have today. We'll limit sort of the geologic timescale to that part for this particular discussion. And what I want you to notice, right, is that we're interested in this part, right, the Hadean part, the first 500 million years of Earth's history. It doesn't look like a lot, right? It's about 1/9 of Earth's history. But it turns out that a lot actually happened and changed during the Hadean. And so if we want to think about some of the global conditions that changed with time, maybe during the Hadean was the onset of plate tectonics. It's not actually clear when the timing of that actually was, right? We know there was some bombardment history, but for those of you who recognize this, the last heavy bombardment over here, which we peg at around 3.8, 3.9, right? There's a question mark there because the late heavy bombardment has also been called into question. But there has to be some kind of bombardment history on the early Earth as the sort of planet is sweeping clear its orbit. And that bombardment likely has an impact on sort of not only the environments, but also the prebiotic chemistry of the planet. And I'm not going to go through all of these, but you can sort of see how these are important, right? The crust evolves, right? There's ocean crust, there's continental crust, it's subaqueous, it's subaerial. All of that has to change. We do probably pretty early on get an ocean, but the chemistry of that ocean, the salinity of that ocean, the depth of that ocean obviously changes with time. The atmospheric composition of the Earth during the Hadean changes with time. Mean surface temperature of the planet changes with time. And I have put all of these on here as cartoons and not meant to be at all real. But one of the things I think it's important to point out is each of these particular parameters has a sort of a temporal mode to it. And depending on the onset of plate tectonics, sort of the temporal mode of that, and the sort of the depth of the ocean, right, you can get sort of different outcomes. And so not only do you need to understand how each of these parameters changes during the Hadean, you actually need to understand how they covary, and you also need to understand when maybe changes in atmospheric composition might have lined up with sort of where we were in the onset of plate tectonics or where we were in our bombardment history. Because all of these things work together to define what the environmental constraints are for any one of these early Earth environments. And that's why this is so difficult, right? It's hard enough to know any of these things during the Hadean, but to know them sort of as a function of time during the Hadean and then to be able to line them up is really quite challenging. So I'm going to go through, this is not necessarily what I know, but just a little sort of overview of what's in the literature on some of these parameters. I'm not going to go into all of this. This is not really the point of this talk. I just want to give you a little flavor. So if you look at crustal evolution, for instance, right, it matters for various reasons, right? If you want some sort of subaerial landmass, right? If you like wet dry cycles, then you really need subaerial landmass, and so crustal evolution is important for that. Also, how the crust evolves tells us what sorts of minerals might be available to do chemistry on the planet. And so what do we know about crustal evolution? Well, this is a figure from Mark Harrison in 2009. There are updated figures since this, but I always like this figure because sort of this area in green is the Hadean, and what is being modeled here is the relative percent of continental crustal volume compared to today, right? And what I want you to note is that during the Hadean, right, each one of these lines is a different model for how much continental crust there was at any given time. And during the Hadean, we have anywhere between 0 and 100% of today. So it's not terribly well constrained. This is why this is called Hadean Uncertainties, right? It's because we have some uncertainties. And even if one of these models is totally right and all others have been debunked, what you can see is that the amount of continental crust also changes during those 500 million years. And so we need a really good handle on how that works. Another really important piece of sort of Hadean environments is the atmospheric composition. And these figures you should all probably recognize. Dave, I'm not sure if you're with us, but you should certainly recognize your own figure and probably your co-author's figure. So the top figure here is a figure from a paper that Kevin Zonley wrote in 2006. I always love this figure because it gives time on a log scale, right? And it essentially talks about what's going on the surface of the planet. And so here's a billion years right here. And you can see that the atmospheric composition changes quite a bit here in what we would sort of call the Hadean. And then there's this new paper out by one of your own, David Catling and Kevin Zonley, that just came out. And you know, I've asked David this before. You've got to start pushing this barrier back past 4 billion. I know how hard it is. I think you have a paper coming out on this now. But if you want to, we would really love to know what this CO2 line, what this methane line, and what this nitrogen line do between 4 and 4.5 billion years ago. Obviously, there's some room for variation here, but that's going to be very important for the conditions that we find on the planet. And so then building on something similar, right, the same paper, people are very much concerned about sort of what the ocean in general, what the ocean chemistry is, but we'll focus right now just on ocean pH, right? This is very important if you're looking at the sort of alkaline hydrothermal vent scenario, right? Part of the alkaline hydrothermal vent scenario is that alkaline hydrothermal fluid emits into an acidic ocean. So that, of course, means that sort of that disequilibrium between an alkaline vent water and an acidic ocean water is sort of part of that sort of drive for prebiotic synthesis, right? That chemical disequilibrium. And so for that, we would need to know something like pH. And again, we have this really great sort of model out of the Catling group. And it goes back to 4 billion years ago. We don't really know, at least I don't have a very good understanding of exactly what the bounds on ocean pH are as a function of time between 4 and 4.5. But it plays a really important role in something like a deep sea vent scenario. And so we really need to understand that kind of chemistry. And so then, to complicate things even more, I will come back to this point, which is that all of these on the left are essentially global parameters. But of course, we're not looking at sort of the Earth as a single environment, right? The Earth is actually made up of a bunch of different kinds of environments, and I've shown those here. And so what we really need to understand are what the fluid composition and rock composition and heat flows are in each of these kinds of environments, right? If we're going to model specific environments, particularly if we want to model all of the specific environments, we're really going to need to understand those. And so what we're trying to do in the Earth First Origins project is sort of take our early Earth team, take our prebiotic chemistry team, right? The early Earth team moves forward with models and geochemical proxies. The prebiotic team moves forward with synthesis experiments. And as we learn, we sort of cycle and move forward together, right? The early Earth team comes up with new constraints, which we sort of put into our prebiotic experiments. And at the same time, the prebiotic experiments might sort of tell us a particular condition that we need to understand, or a particular environmental parameter that we need to understand. And together we sort of march through this sort of parallel pathway, trying to build up both of our understanding of the early Earth, but also the conditions that lead to prebiotic synthesis that might have select. And part of the challenge here is figuring out how all this parameter and project, in addition to having this early Earth team and the prebiotic team, what we really have are two pieces of the gateway to early Earth. One of those pieces is the virtual early Earth portal. And in this portal, what we're trying to do is we're trying to constrain the possibilities for different environments and their conditions during the Hadean, but we're also using geochemical models so that we can understand better how conditions can co-vary, right? So we know with depth, temperature and pressure vary, but even more importantly might be the mineralogy of the crust and the sort of fluid composition of fluids that are interacting with that crust. And so inside the virtual early Earth portal, we have essentially spaces where folks, and this is not only our team, but anybody out there, obviously when this gets built, we're working on the development of this portal right now. But what we're trying to allow people to do is sort of go into a virtual space and say, okay, well, I'm interested maybe in an event system, but I want to know what happens, right, as fluid flow changes. And so you can set the kind of mineralogy you have, you can set your CO2-CO ratio and change fluid flow, and you can decide what you want to model on the backside of that. Maybe in this case, we're showing temperature, right? So you can put any sort of output parameter here and any input parameter here, and you can sort of consider these things to be little knobs that you dial depending on sort of maybe what time of the Hadean you're thinking about, or the latest paper that came out on what we think crustal composition is. And so that's the virtual early Earth portal. And in conjunction with that, we have the early Earth lab. And this is where we take all of these environments and we try to build them, right? And so here's just a bunch of pictures of some of the equipment in our lab. I'm gonna walk through this sort of quickly. I just want to give you a little bit of a tour of some of the equipment that we're building in the early Earth laboratory. Most of the really deep stuff, really high pressure stuff we'll do in the piston cylinders. These are sort of tried and true, really good for geochemical proxies. These are largely housed here at RPI in Bruce Watson's lab. But as we sort of hit some of these deep, but not quite that deep environments, we're really looking at the sort of maybe the 200, 300, 600, 700 bar range. And we have a bunch of different kinds of equipment that can live in that pressure range and replicate things in that pressure range. So we have these small Bodmer devices, and this right here is a sapphire window, so we can do some in situ Raman experiments. Small volume batch reactors that can get to pretty high temperatures and pressures. It's largely to look at sort of water rock reactions. And then both of these are from Tom McCullum and Jeff Seawald, right? These are either flow through or flexible cell reactors that also help us look at water rock reactions and maybe organic synthesis in those systems. Moving into slightly cooler temperatures, right? And so we're sort of in this upper aqueous part of this diagram. We have classic hydrostatic pressure vessels. We have this new variable volume pressure vessel which has a floating piston in it. We've also developed this large volume flow-through reactor that allows us to mix fluids. This can be a two-phase system. We can also do flow-through in these push reactors by taking the piston out and packing them, so we can make these packed column, high pressure, high temperature systems. And then, because there might have been subaerial land, we also have developed a few different kinds of experimental sort of approaches to capture these three-phase systems, right, where there's solid, liquid, and a gas phase. This is a picture from work that's coming in just like 10 slides or something, so I'll show you this. But these allow us to essentially build a Hadean atmosphere in the presence of two other phases. We can also do this at higher temperatures and higher pressures by using a three-phase flow through. And so that this device on the right is also currently being built. And so the idea here is if we take the virtual early Earth portal and the early Earth lab, and we put them together and apply them to this Earth first origins approach, we can get this part right, or as right as we can get it right now, given what we know about the Hadean, right? We can get these environmental conditions right, and we can have our laboratory experiments actually really look like the Hadean, right? And that's a big step forward for prebiotic chemistry in general. And so that's our approach. And what we're hoping is if we take this approach, we can hopefully find our way through this. So this diagram on the right-hand part of it is all of the stuff that, you know, various worlds and hypotheses and scenarios have come up with in terms of molecules that might be important. If you synthesize all of this information, most prebiotic sort of pathways start with very small inorganic precursors. They go through simple organics, and then monomers and intermediates, and then polymers, and then something functional, right? And so they go from very simple to very complex, right? And so we're hoping that we can replicate this pathway for all of these different kinds of molecules by getting these Hadean environments right. And so that's sort of the first half. I know I'm more than halfway through my time. I'll try and get through this a little quicker. But the conclusion to the first half is, I mean, we haven't done all of this yet. And so in some ways my conclusions are, you know, build it and they will come. So this is what we're going to try and do. We're going to build the gateway to the early Earth. We're going to take this approach, and hopefully this will be broadly useful to the entire astrobiology community. What I want to do in the next bit here, and it's not really a half, I promise I'll get through this pretty quickly, is I want to take one example and just show you what we've been doing in the lab. And we're going to take nucleic acids and nucleotides as an example, and we're going to look at the process of polymerization. And this, you might think, oh, well, she's an RNA world person. I'm not an any kind of person. I am just interested in what kind of chemistry happens in what kind of Hadean environments. And so we're looking at polymerization and dehydration reactions. And nucleotides and nucleotide polymerization is a pretty easy system to deal with. So here's a nucleotide. It's made up of a ribose, a nucleobase, and a phosphate. The four canonical nucleobases are over here on your left. There are a bunch of non-canonical nucleobases. We've looked at a few of those, but we've not done a lot of that work, and I won't be showing that today. But the idea here is how do you take a nucleotide and go into the laboratory and make a polymer, right? And so here are 3 nucleotides in a row, and here are the waters that have come off of those reactions. Now, we're not the only ones who have done this. People have been doing this for decades. And after 50 years or so of work, this process has been optimized. And one of the best ways to do this is to take your nucleotide and attach imidazole to it, which, by the way, is very hard to do in an aqueous system. Can be done, but very difficult to attach an imidazole to a nucleobase. Put it in the presence of a very specialized, very well-treated clay, and you can make an RNA polymer. So this here on the right is really the optimized lab conditions. There are a few other conditions where you can make RNA polymers. They're sort of listed here. So most of the ones on the left here, the white is what you're looking at. And the height of this bar is the length of the polymer, right? So you can make relatively long polymers in the presence of uranyl nitrate. You can make long polymers in the presence of treated montmorillonite, but without any catalyst around, you essentially get about 2, maybe 3, depending on what you have. And you can get some polymers in like lead chloride. But this gets us back to this problem, right? You can't, even if uranyl nitrate does a great job, uranyl nitrate really isn't all over the planet, right? And this very, very treated montmorillonite does a good job. It's really unlikely that we're going to find that in any sort of abundance on the planet. And so this is sort of where this stood when I started here at RPI. And so we decided to take this process and replace this laboratory with something that hopefully looked a little bit more like the Hadean. And we were not able to go straight from this sort of single montmorillonite imidazole activated experiment straight into a full-on Hadean environment because we just didn't know enough about how this process worked. And so instead what we did is we started to break down this problem. And so we asked 2 questions and looked at a few different variables, right? And so this, by the way, is all work that was done by my former graduate student, Vince Riggi. He's now at the Geophysical Lab at Carnegie Institute. And so this is primarily his work, and I want to make sure that he gets credit for all of this. And so we asked the question about catalysis, right? So other than montmorillonite, are there other good catalysts for polymerization out there? And then what do environmental conditions like the headspace, the pressure, and the temperature, how might those impact polymerization? And so I'm actually going to go through all of these with you. I'm going to do this as fast as I can, but there are a lot of data here, so just bear with me. The overall picture is what I want you to get. I don't need you to sort of know every single detail. So the first thing we looked at are sort of minerals, right? Treated montmorillonite is one thing, but I'm pretty sure that the planet is made up of lots of other minerals. And so we essentially went in and said, okay, what other minerals are there? It's a geology department. So we literally just rated what we could for our rock and mineral library and started crushing them up, putting them together with RNA monomers and let them go. And we did this at various temperatures and pressures. I'm going to start with just the 25 degree and 1 bar data. And here are all of the minerals we looked at. In these bar graphs, what you're looking at is the height of the bar essentially gives you the length, the maximum length of the polymer that we observed. And so over here, this is untreated montmorillonite. We got a polymer that was 5 nucleotides long. Over here with galena, we got a polymer that was 5 nucleotides long. The orange lines, they're all sitting at 2. And that's what happens when you get a dimer when you just put the monomer in water. And so the main takeaway from this is that most minerals, right? Looked at all the tectosilicates over here, bunch of other sort of random minerals over here, the oxides down here, most of them did not actually contribute to polymerization. What did contribute to polymerization? Several of the clays. The metal sulfides tended to contribute to polymerization. 1 or sometimes 2, depending on the day, zeolites. And then over here, what you can see is that halite also gave a bit of a signal. And we did both halite and just before halite saturation. And so we started to understand that there was, first of all, more than 1 mineral out there that can catalyze RNA polymerization. This is really important. And what we did next was we said, well, this is at 25 degrees and 1 bar. I wonder if anything else matters. And so these are some results of different minerals being used as catalysts. Same type of setup, right? Each of these bars indicate the length of the polymer that was the maximum length of the polymer that was generated. But in this case, we did our experiments at a number of different pressures. And we did this mostly out of curiosity, right? We wanted to see if other environmental conditions matter. And so treated montmorillonite is what you see over on the left. It is unaffected by pressure until you get to about 10 kilobars, which is really relatively high pressure. Now, what I want you to look at next are these dark blue bars. These are the 1 bar experiments, right? And they're generally giving between 3 and 4, sometimes 2. In these experiments, 3 was about our sort of negative, no catalyst control. And so if we just did these experiments at 1 bar, we would have said that calcite and aragonite and nontronite and pyrrhotite and this random black smoker we had and lizardite and anorthite, none of these are catalytic. So then we tried these at a bunch of other pressures. And some of these, I admit, are relatively high pressures. But what you'll see is that the calcite and the aragonite, both of these are carbonates, right, have a catalytic ability at elevated pressure. Now we're working on why this is true, but the point here is that you can't just do one experiment at one set of conditions and conclude sort of all conditions from that. If we had done that, we would have said that carbonates are not at all catalytic, but it turns out carbonates can indeed be catalytic. And this is sort of why I show these data in this way. So there are minerals other than montmorillonite that are catalytic under certain conditions, right? So we know the sulfides are catalytic. We can see that a little bit in the pyrrhotite, and it turns out that the carbonates are catalytic as well. Okay. So that's one thing down. We also looked at aqueous metals, right? And here are, so in this set of experiments, these are entirely aqueous phase experiments. So there is no solid mineral surface catalyst in here. So we just have the nucleic acid monomer. And then we tested a bunch of metals as chlorides. And what we did here is we did each of these metals from a very low concentration, increasing the concentration until we hit saturation. And so what we're thinking is happening by including sort of how aqueous metals work as catalysts is we think that the big giant cation floating around in solution, represented here by this orange ball, essentially attracts the monomer, right? Pulls in probably the imidazole end, and allows this dehydration reaction to happen, right? So you get two of these monomers together, the water leaves. The imidazole stays attached to the cation, and in this case, it's a dimer that essentially leaves. But what's really probably happening here, right, is this close association between these two monomers and the cation reduces the local activity of water. And by reducing the local activity of water, you're able to actually do a dehydration reaction, right? Because the bulk activity of water is relatively high, but the local activity of water is relatively low. So that was our hypothesis. And here are a bunch of the data. And so here what we're showing on the y-axis is the maximum oligomer length. And we're showing that as a function of metal concentration up to saturation. All right, and so all of these x-axes have different units on them because we're going just to saturation of the metal chloride. And so I won't belabor you with each of these numbers, right? But, you know, manganese over here does pretty well, magnesium does well, calcium does okay, gets you up to about 5. This second set of data is a little different, but also really interesting. So calcium does well in these moderate concentrations. Lead does really well at a relatively low concentration. And then I want to point out this last one. I apologize that there's not a line on it, but this is the iron data, right? And so this is actually on a log scale, the iron concentrations. And there's also a maximum here at about 10 millimolar. So summarizing all of those data, you can see that the aqueous metals can be good catalysts. They fall into 2 groups, right? There are the groups where the maximum ligament length just sort of asymptotes, and then there's another one where it peaks out at some moderate concentration. These are the maximum oligomer lengths that we found over the entire concentration range. And so if you just saw this, you would say, wow, well, lead's your best bet for something like RNA polymerization on the early Earth. But if you take estimates of what the likely metal concentrations were in early Earth, maybe earlier seawater, and you look at the sort of oligomer lengths that match those particular concentrations, you get a different story, right? In this case, it's calcium and iron and maybe sodium that are your biggest contributors to polymerization under sort of Hadean conditions. And that's really quite sort of intriguing, right? Because those are the things we actually expect under Hadean conditions. So, okay, so we've been through both catalysts I'm going to run through headspace, temperature, and pressure, and then I will try and wrap it up after that. So we were interested in sort of what the gas composition of the experiment, if it had any particular, if it had any effect on the polymerization outcome. And the reason we were interested in this is because, as I was saying to the graduate students today, something like 98% of the prebiotic chemistry experiments that are done in water that's equilibrated with the current Earth's atmosphere, right? So it's equilibrated with 20% oxygen. And when you're talking about organic compounds, which are particularly redox sensitive, I've just found that to be inaccurate to do. And so we did a set of experiments where we essentially had sometimes our mineral catalyst, sometimes a metal catalyst, in this case calcium, in an aqueous solution, and we swapped out the headspace, and we looked at both a headspace of N2 and a headspace of CO2. And we did this for all of the 4 canonical nucleobases, and this is what we got. So we're showing here modern atmosphere, right? And so that's on the 4 bars on the left. And then where our headspace was nitrogen, and then where our headspace was CO2. And each one of these is the maximum oligomer length for each of the 4 canonical nucleobases. And so what you can take away from this is, and this is with montmorillonite as a catalyst. And so what you can take away is that there's very little difference between the modern atmosphere and a nitrogen atmosphere. But there's a huge difference with a CO2 atmosphere. We actually think that the CO2, the real effect here is from a lowering of the pH of the solution. Our pHs in these experiments weren't actually buffered. And so we did the exact same thing with calcium chloride as a catalyst, and we got the same pattern, even though the overall oligomer lengths were lower, right? And so the modern atmosphere and the nitrogen atmosphere gave about the same patterns in oligomer lengths, and then the oligomer lengths were much inhibited under CO2. And so the baseline, by the way, this is given by these dark lines, baseline did not change. There's no significant difference between a modern atmosphere and a nitrogen atmosphere, but the lengths decreased by quite a bit in the presence of a bar of CO2. That's sort of spurring on a bunch of experiments that we need to still get after, where we try and buffer the pH and see what we get when the pH is buffered, but we still have a lot of CO2 around. So the last thing I want to talk about is temperature and pressure. And so in this set of experiments, what we were really trying to get after was the idea that not everything happens on the surface, and even on the surface during the Hadean, it's unlikely that the total atmospheric pressure was 1 bar the entire time. And so we really do need to consider pressure as an environmental parameter. And of course, we need to consider temperature as an environmental parameter. We know that the temperature, the global sort of mean temperature changed during the Hadean, but in addition, if you look at all of these different kinds of environments we expect on the early Earth, they all have a wide range of temperatures. And so again, what we've done is we've taken our RNA monomer, our either a aqueous metal catalyst or a montmorillonite catalyst in this case, and we've done these 3-day experiments at a variety of temperatures and pressures. Our temperatures went from 25 to actually 85. And we went from essentially atmospheric pressure all the way up to a kilobar. And all of these were done in our static pressure vessels. And so I'm going to run through these data really quickly. The white data points are the maximum oligomer length at a kilobar. The yellow data points are the maximum oligomer length at a bar, and we're showing these as a function of temperature. And so what you can see for non-treated montmorillonite, you get somewhere between like 5 and 6, and there's a slight decrease in length as a function of temperature. If you use treated montmorillonite, you get a similar kind of story, even though the slopes here are a little different. If you use a 5 millimolar lead chloride solution, there is a sort of starker effect of increasing temperature on oligomer length. But if you use a 1 molar calcium chloride solution, which is sort of our go-to positive control, temperature doesn't have much of an impact, but there is a difference here between the 1 kilobar and the 1 bar data. And so if we look at these all together, this is what we get, right? These are just those 4 lines for each of those catalysts. And what one takeaway from this might be is that, well, temperature, sort of elevated temperature, can inhibit polymerization. But what I take away from this is something a little bit different, which is that all the way up to 85 degrees, our catalysts are still pretty good catalysts, and we're still getting polymerization, right? For treated montmorillonite, we're still getting oligomers that are about 9 nucleotides long at 80 degrees. That's significant considering, you know, sort of what the temperature ranges might be in various early Earth environments. And so, unlike sort of what you may have heard, which is that organic compounds are unstable in hydrothermal systems or at elevated temperature, this is clearly not true. We're still doing polymerization all the way up to 85 degrees. So I'm going to sort of, this is what we've done, right? So we've talked about minerals, aqueous metals, headspace temperature, and pressure. I'm going to tell you this, which is that we also started looking at sort of covariance across these, right? We even did sort of a bunch of aqueous metals all together, trying to understand what polymerization might have looked like in the Hadean Ocean. I don't have time to go through all that today, so I'm gonna skip those very confusing data. Hang on, I'm trying to skip those very confusing data. I just don't wanna sort of make us go too late. I know it's already 4 o'clock on your end. Let me just, oh, it's very slow getting through this lovely thing. So I'm gonna skip the Hadean. I'm just gonna go to the end here, right? So we did a modern synthetic seawater, right? Where we put a bunch of the aqueous metals in modern seawater sort of composition, and we did a polymerization experiment. And what we got was a 3 nucleotide long polymer. And then we did it for a synthetic Hadean seawater, right? Now, there are some sort of bounds on what Hadean seawater is. We picked something, right? Just to sort of do a quick experiment here. And what we found was that the sort of high iron concentrations that are predicted for Hadean seawater can give us oligomer lengths up to about 5. And so 2 conclusions from this were, which one was that sort of having other cations in the mixture did not inhibit polymerization, but having other cations also, polymerization wasn't additive, right? And so you didn't get the 5 from iron plus the extra 3 from calcium chloride. You sort of maxed out at that single maximum oligomer length. So our conclusions from this sort of test case scenario for this Earth First Origins project, where we were just looking at nucleic acid polymerization, is that several minerals can catalyze polymerization depending on the conditions. Aqueous metals can catalyze RNA in the absence of a solid mineral surface. CO2 is inhibitory, likely due to a lowering of the pH. Increases in temperature can moderately curtail polymerization, but do not stop polymers from being made. And finally, elevated pressures minimally affect polymer length. And so those are just sort of some of the takeaways. Where we're going next is sort of trying to take a similar approach, but much more complicated and much more expansive, right? We're looking at all of these conditions on the Hadean Earth. We're trying to constrain those a little better with the virtual early Earth portal. And then instead of just looking at nucleotides and nucleic acids, we're kind of going to look at all of these sort of potential prebiotic molecules. So obviously we have a lot ahead of us to do. Yes, we do have spaces for graduate students. So if you're an undergrad out there, please give me a ring. We were supposed to have faculty positions. I imagine there will again be faculty positions in a post-COVID-19 world, but right now we're not really allowed to do anything like that. So hold tight on those. But I do think what we have here is something really exciting, and I'm hoping that sort of laying this out has gotten some of you excited, gotten some of you thinking about what you might do. And honestly, once the Early Earth Lab is sort of finished and built, it's really going to be open to anyone. And so if you have your favorite biomolecule or your favorite environment or your favorite gradient that you want to investigate, we should have the ability to sort of help you out with that and help you get your experiment done. So I think with that, I'm probably just a little over time. I will say thank you, allow you to do whatever it is you do, unmute, ask me all your questions. And really, I want to sort of thank you for listening. This is really fun.
All right, great. Thank you very much, Karyn. On behalf of all the audience, I'm going to applaud for you. They're all applauding for you in their own rooms, but that was fantastic. Thank you so much.
Thank you.
Even some virtual claps I see in the people's icons there.
Perfect.
So as I said before, if you have a question for Karyn, please type that into the chat room right now, and I'm going to ask her the question. So we've already got a couple here already, so I'm going to get started. So first up from Mike Wong, he says, thanks for the great talk. I love your approach towards the emergence of life, but he does have two questions. Number one, will your experiments also explore conditions on other worlds? It would be really interesting if non-Earth conditions were even more successful at generating exciting chemical systems.
Yes, so I'm gonna see how good I am at going backwards here. I have 3 screens, so don't be offended if I look away. Here we are. So this is, right, so this is sort of the early Earth laboratory. The conditions here go from about ambient temperature to, well, in the piston cylinders, we can go pretty high up to sort of melt temperatures, right? So we can melt rock, so that's pretty good. In the rest of these experiments, we can go sort of in the aqueous phase up to a couple hundred degrees and a kilobar. And so from a temperature pressure perspective, absolutely, we can sort of jam other, not all other planetary conditions, but some other planetary conditions in there. It's not part of our project. It's not because we're not interested in that. It's just because we're limited in the us, right? The hands-on part of us. And so, yeah, I think we could jam it in there, and depending on what the condition is, and I think it would be a really fascinating thing to do. If any of this is useful for anything, I mean, one of the things I've learned doing high pressure work is that you don't want everybody in the world to build a high pressure lab because it's really, really hard to do. It's really hard. And so we would rather just have people be able to come use this and get some really interesting experiments done without having to go through the 10 years of pain of figuring out how to build a high pressure lab. So if you have a planet, bring it.
Great, all right, thank you. Mike's second question is, are your experimental setups open systems? I ask because as far as I understand, maintaining environmental disequilibria seems essential for driving ever-increasing complexity.
Yeah, that's a really good question. We have the ability to do flow. So we can flow in a 2-phase system. We can flow in a 3-phase system. So in that case, they are open. We do have the ability to mix 2 different fluids in the large volume flow through. It's hard, as you know, right? The beautiful thing about black smoker chimneys that we see at the bottom of the ocean is that they build these beautiful black smokers as minerals precipitate, which is great at the bottom of the ocean and really, really bad in high pressure lines. So we can sort of replicate this fluid mixing that you see at the bottom of the ocean, but it gets to be a challenge because you do end up precipitating minerals. And so it's tricky, but yes, we can do it.
All right, thank you. All right, next up is Craig Moyer, who asks, would you consider serpentinization environments, i.e. serpentinite extruded mud volcanoes, occurring at early plate boundaries as being a viable lower temperature location to have promoted the transition from prebiotic conditions to the evolution of living cells?
Hi, Craig. It's been a long time since I've seen you. I really miss you. We had a great cruise, and I don't even know how long ago that was, but hi. Yes is my answer to your question. I'll try and say more than yes, but serpentinizing systems, both sort of deep sea classic sort of lost city style serpentinizing systems, as well as sort of the mud volcano systems, I think those would be really interesting. The nice thing about serpentinization systems is you get the sort of reducing power of the hydrogen that's produced. And that just, if you can grab that reducing power and kind of quench it at low temperatures, then you have a whole lot of potential to do abiotic organic synthesis. And so I would love to do sort of the whole suite of everything from mud volcanoes to sort of your classic ultramafic rock system in here. I think we could get some really interesting prebiotic chemistry out of that if we can do the thermal gradient right. I really do.
Cool. All right. Next up is Zach Cohen, who says, super cool talk. Do you know how the various metals or minerals change the distribution of RNA products that you measure? So the relative concentration of monomers versus dimers versus trimers, for example.
Yeah, that's a really good question. I will, so the short answer is no, but I'm going to expand on that answer and give you a little of the dirty side of doing RNA polymerization experiments, which is that we measure the length of our polymers using MALDI-TOF, right? So it's matrix-assisted laser desorption, time of flight mass spectrometry. And MALDI is really great for getting a good idea of sort of polymer lengths. You see dimers and trimers, and you see peaks, very distinct peaks. You can see if they're linear or aggregated, if they've made a circle because you lose a water. They're really, really good at that. But what MALDI is really, really bad at is being quantitative in any kind of way. And so we don't have a really good idea of how much of any length that we're getting. We're trying to develop those methods now. We brought in a new analytical chemist a few years ago, and he's a really good analytical chemist. And so we're trying to get after this with some electrospray ionization mass spectrometry. Don't ask me much more than what that is, because that's what I know. That's why we hired the analytical chemist. But we're trying to get after these sort of concentration and sort of quantitative analyses, because we do sort of run short using MALDI-TOF the way we do, because we can't get those concentrations. So I would love to, but I don't have it yet.
Great, thanks. All right, next up is David Catleen, who asks, how do your nucleotide polymerization and oligomers results compare with those of others who have done polymerization with wet-dry cycles, e.g. papers authored or co-authored by Dave Seamer, which I think he maybe meant to type Dave Deamer.
No, it's Deamer and Damer. They do that, they work together, and it's just to confuse us, yeah.
Well, he said Seamer, so I think that's the typo. But maybe I'm wrong. Maybe there is a David Seamer out there. Whose setup should we believe represent what was actually prebiotic synthesis, and how will we decide?
So those are great questions, David. So to my knowledge, Damer and Deamer have not done RNA yet. They've done a bunch of other things. To my knowledge, they've not done RNA yet. What we've done for montmorillonite, our maximum lengths when the montmorillonite is treated and the adenosine is imidazollated, we usually get about 13. That's actually what the Ferris lab got for most of their time here. As a caveat, the Ferris lab did once publish 55, but it turns out that was actually an analytical artifact. They really didn't get 55. So we get sort of up to those maxima of about 13. That's in a single batch 3-day experiment. One of the things we're doing right now, and I really shouldn't give this part away, but one of the things we're doing right now is we're saying, okay, well, if you can make a hexamer, right, which we do all the time in just sort of calcium chloride solution or something, if you can make a hexamer, well, what happens if you then have 2 hexamers together? Can you actually make a 12-mer, right? And how many polymers can you sort of put together? That's the next step, because right now it seems that all of our polymerization is being done sort of one monomer at a time, and it's being done in a single batch experiment. One of the things that the wet-dry cycles do is they sort of continues, it's sort of like a refresher experiment all the time. except the refresher is increasing the concentration, right? And so we're sort of taking a similar tack. We're trying to do these sort of similar refresher experiments. We don't have the data out. We got kicked out of the lab, as you know. So I don't have an answer, a good comparative answer for that. But one of the, to answer your last question about who's right and who should we believe, what I would say is that any experiment that can do a really good job of replicating the temperature, pressure, chemistry, sort of the whole environmental condition that really represents, sort of faithfully represents an early Earth environment is just that. It's an experiment that accurately represents an early Earth environment, and therefore the chemical outcomes are sort of is chemistry that represents chemistry that could have happened on the Hadean. I don't really think about this as right and wrong, right? I might get 13, Dave might get, 18. We might figure out a way to get something else. We might be able to make liposomes in a different environment. I think we need to understand sort of the chemical trade space and the environmental trade space first before we start taking one experiment or one biomolecule like an RNA polymer and sort of going all in too soon, right? I still think we need to sort of map the parameter space first. And so I think that any experiment that has good conditions is right. And so you can pick them all. You don't have to pick just one. So you can pick all of us.
Great, thanks. And I'll just clarify that later on in the chat, David did say he was auto-corrected, and he did mean Dave Deemer. So
excellent.
For you. So that was correct. That was a good answer. That was the right answer there. All right, so moving on. Next is Stuart Bartlett, who says, great work, thank you. Are there any plans to run an experiment where you simply prioritize faithfulness to early Earth conditions, and you don't necessarily monitor for efficacy of a particular reaction, but you simply simulate that environment and observe what it does in as much detail as is feasible?
Yeah, no, that's a really good question. That's sort of the beginning of this idea, right? And so we do have a bunch of experiments designed where we don't start with anything, right? I mean, the precursors would be CO2, N2, right? Those sort of the things we know are in the atmosphere or dissolved in water. We could get sort of a typical hydrothermal fluid if we could, get a Hadean hydrothermal fluid composition and just run it. That is the idea, is just build the environment. The very first set of experiments is to just build the environment with the simplest precursors, no real monomers, nothing sort of that sort of complicated yet. The one thing that is that's hard, that makes that hard, it's the thing I've wanted to do, and it's sort of all I want to do. But the thing that makes that hard is when I go to my analytical chemist colleagues and say, hey, I'm going to run this experiment and I want you to tell me what's in it. And I'm hoping for some kind of organic compounds, but I don't know what. They say, well, what are you looking for? Are you looking for organic acids or amino acids or, PAHs? Or it's like, no, I want to know everything. And it's very, very difficult. Like this is a very hard analytical problem. It's hard to look for everything. All right, it's very hard to do the identification of the molecule on the back end. So we are going to do this, but the analytical part on the back end is going to be challenging. And so it's just a caveat to that suite of experiments. When it comes to things like monomers and polymers, or looking at sort of making particular pieces, maybe of the RTCA cycle or something like that, it's a little easier because you know what your expected product is, and it's just an easier analytical task when you can tell them what the sort of expected product is. But we are gonna do this. It's a fantastic idea. We need sort of an army of analytical chemists on it, but we are gonna do that. Yeah, it's really just what you want to get after. I totally agree.
Great, thank you. All right, next up is a question from Roy Black, who asks, Has anyone looked at the effect of pressure on vesicle formation?
No, but I've been talking about this with a few colleagues for a while. I'm just so excited. They're all like, can I bring my liposomes to your lab? And yes, absolutely, bring your liposomes to my lab. But to my knowledge, nobody's looked at that. I have talked to some folks about it, but to my knowledge, nobody's actually looked at that. I think it would be fascinating to do. I would love to do that. You know, when you get to do experiments like this, you are generally high on ideas and sort of low on bandwidth, sort of available bandwidth, but vesicle formation is on the top of my list. Yeah, so bring your vesicles.
All right. Next up is somebody who's identified themselves as Stitzel, who says, perhaps putative oceanic serpentinization reactions occurring on Enceladus as well. That might be a follow-up to Craig Moyer's question on serpentinization. So I don't know, have you been thinking about serpentinization in Enceladus?
I have not, but sort of much in some ways, it's the same answer about all the other planets, which is, you know, so many planetary environments and so little time. I would love to, but we're just going to need more hands and more people, and you know. But yes, I think serpentinization on other planets, other bodies like Enceladus, I think that would be really interesting to do. I would need to know more about the conditions there, or whoever that is. I think it might be Marshall. Would have to come and help me. But that's all good. I would love to do it. That would be fun.
Yeah, great, thanks. Yeah, you're probably right about who it is. Next up is Shintaro, who asks, how low temperature do we extrapolate the temperature dependence of the polymerization? This question is because the surface temperature on the Hadean Earth might be cooler than the modern Earth.
Yeah, so we went down to, so in the data I showed, we went down to ambient lab temperatures. We have done experiments at 4 degrees as well. Those polymer lengths are actually just a little bit shorter than they are at 25 degrees or ambient or at lab temperatures. And we haven't done the follow-up on that, but I'm wondering if we just actually let that experiment go for longer, right? It's just probably a little kinetically slower at 4 degrees. In terms of going lower than that, I don't normally go in that lower direction. We could, I think that those experiments would just have to be longer because kinetically they're just going to be that much slower, unless you're looking at sort of a nice sort of maybe eutectic phase boundary or something like that. But we could go in that direction. That's sort of not part of what we're considering here, but it's a really good idea to do. Well, the lowest we've gotten is 4.
All right, thanks. All right, next up is Arsudi, who asks, what do you think about the possibility of bombardments introducing metals or minerals which could be catalytic and help polymerization? How can you replicate conditions and changes caused in environments by bombardments in the lab? That's
a great question. I'm working with Simone Marchi right now on that question. And so some of the questions we're considering there and how we might do it experimentally, we're looking at how in like impact generated hydrothermal systems, what sort of water rock reactions might give us in terms of mineral alteration and metal leaching, right? That's clearly going to depend not only on the mineral composition of the impactor, but also the conditions of the alteration. In addition to that, though, that fluid rock reaction is also going to sort of produce some amount of disequilibrium, right? And so we're looking at sort of how the hydrogen generated from fluid rock reactions with an impactor, for instance, with native iron in it or other reducing metals, that those water rock reactions are likely to produce some sort of reducing power. And so we're going to try and mimic that in a flow-through system in the lab, right? And so it would really be mimicking essentially water rock reaction in an impact generated hydrothermal system. but in addition to sort of those broad environmental questions, right, it's essentially a whole different environment that we have to try and replicate in the lab. There's a compositional difference here, right? So impactors can bring metals. Impactors can also bring various, sometimes simple and sometimes more complicated organic compounds. So we can also look at how those organic compounds might be transformed once they reach the planet. And then there's some other work I think you might know by Matt Pasek, and Matt has suggested, I think it's Matt. It's late in the day, but sorry, my brain is leaving me. He suggested that, you know, impactors might be a really good source of phosphorus, right? And so there's a reduced phosphorus mineral, schreibersite, that might contribute to phosphorylation of organic compounds. And so there's a lot there that that we really need to dig into in terms of sort of impactor experiments and impactor chemistry. It was outside the scope of this first project that I just described. I mean, that's why I'm working with Simone and Everett to try and sort of build the impactor part of this. Again, you get sort of limited in the number of people and experiments you can do. And so we're trying to build out a whole impactor part, because I think that contribution could be really significant. And depending on what sort of the impactor model sort of is in terms of frequency and distribution, it could be a pretty significant chunk of material on the surface of the planet during the Hadean. So yeah, we're looking at that as well. So call up some folks and tell them to fund us.
Thanks. And Matt does love phosphorus, so I'm pretty sure you're right that it was Matt.
Yeah, I just, you know, it's sort of cloudy up here. I know it's the afternoon for you guys, but it's like 7:30 here. It's like, my hand is empty.
Well, I have good news on that front then, Karyn. This is the last question.
You know, I'm really having fun. If I had a beer, I could do this all day. So keep asking and just have the...
I said that somebody just popped up a new question, so maybe this is the second to last question.
Oh,
so
good.
anyway, next up is C. Davis 45. Not sure who that is, but they say, great talk. You mentioned earlier that your lab is trying to be agnostic in terms of the different camps of the origin of life. The technical side of your talk was mostly about RNA polymerization, but will your lab also investigate other avenues to the formation of life, such as lipid membranes or metabolic pathways?
Yeah, we have, I'm always wary of including the RNA example as the example, right? Because it makes it look like that's what we do. We're working on a bunch of those other camps, for lack of a better word, as we speak. In fact, we were developing these experimental protocols right before we got kicked out. And so, yeah, we're looking at sort of all of these things. I don't have a lipid person yet, but the pieces of the metabolic cycles are kind of the next place to go. I think, as you know, Lori Barge at JPL works on this a lot. And she's done a lot of really, really interesting work. And so we're going to try and sort of build off of that and move those sorts of questions into these sort of experimental setups. So that part is absolutely coming up. We're working on amino acids right now. We've actually done some work. I didn't show it here, but we've done some work on prions as well. So don't even get me started about prions. They're really scary. I don't work with the scary prions here, but still the idea of having prions, but we've done it. So we are kind of exploring all of these sort of places. I just showed you the one because it's easy to sort of containerize for a talk, but there's lots of other stuff. All camps shall be equally represented. Even things that aren't camps yet shall be represented. I do not want to pick sides.
Great, and so the comment that came into the chat room when I just put in you guys started was actually from Stitzel again, who's identified himself as David Stitzel, who just basically said that another bombardment might be that from asteroids and meteors that may serve as a seeding of life on the planet via panspermia. And then goes on to say, awesome presentation, great Q&A. Thank you for your time and insight. And I think that speaks for all of us. Thank you so much, Karyn, for being a willing participant in our virtual seminar series this quarter. A really fascinating talk, and really appreciate the time you've taken to spend with us, especially because it is getting so late there in New York. So,
Well,
thank you again.
Thank you. I just want to say thank you. I've like I said at the beginning, I didn't know how well this was going to go, and I was sort of missing that I wasn't going to see all of you, but I really feel like I have been able to interact with you all today, and it's been really, you know, when you leave after you've given a seminar, right, you've visited, you get all kinds of excited because you've talked to all these new people. I still have that same feeling. So, and I'm not jet lagged. So, so really, thank you everybody for sort of going online and doing it this way. I've had a blast. I really, really have. It was good to see and hear from all of you, and I hope that I can be there in person someday. I'll make a plug for the fact that I did just get back. I told the students this today. I just got back from the Mid-Cambridge Rise doing some high pressure microbiology. So after the labs get up and running again, I'll have a whole different talk that's on a totally different topic. I can come and actually go in person and sort of, you know, share all of that data with you. No RNA, all microbes, and maybe I get to see you guys then. So thank you really for a fantastic day. Really.
I'm so glad to hear that it worked out for you, and we'd love to have you here in person sometime in the future.
Sometime we will make it happen. That's perfect.
Yes, we will indeed. So until then, keep up the great work, and we'll look forward to more great discoveries from you and your lab. So thanks again for coming out here.
Thank you. Thanks very much. Appreciate it.
Bye.
Bye.